Hey, how's it going? My name is Stefan Bidwolf. I'm a grad student at UC Santa Cruz, and in this tutorial I will show you how to download data from Ncbi. There's a couple reasons why you'd want to do this. It might be that you want to compare your data set for microbiome, transcriptome, proteome, or whatever work to another data set that's publicly available. And you might need to download like hundreds of files or lots of different ones, and it's not so simple to understand how to do that. I haven't found a video that made it super clear. So I'm just going to share with you one way to do that, and we're going to be working specifically with metagenome data that we can use for QIIME2 for bacterial diversity analyses and so on. So I've got some code running here, and I'm sorry I'm going to be looking this way. This is where my actual computer screen is. But I've written some code that can help you go through all the different steps. And so what we're going to do in this video is work through these steps as quickly as possible. And if you want access to this code, please let me know and I will go ahead and upload that somewhere where you can access it. But some of the first things you're going to want to do before beginning this tutorial is to install Miniconda, Bioconda, GNU Parallel, SRA tools, which is Ncbi's tools that they use to allow us to do this downloading. Feel free to read this quick guide, which I found after I made this tutorial, and then download QIIME2. All right, once you've done that, you'll just go through these steps here. So I'm going to be creating a directory here called Ncbi data. Then I'm going to cd into that, so change my directory into the Ncbi dataset. And I'm sorry, just to backtrack real quick. We are running Bash, so this would work on a terminal in Macintosh. If you're using Windows 10 like I am, I highly recommend you download the Windows subsystem for Linux, and then use that Windows subsystem with Visual Studio Code, which is this program that I'm using here, so that you can have an integrated development environment like we're looking at on my screen. So I've got, code that I've written here, and by pressing Control and Enter, I can actually execute this code. So we've cd'd into that, and I'm going to make this directory called Pollock. And the Pollock directory is, I just named it that because we're going to be downloading the data from Pollock's paper. So with that done, we can now go to this link. This is the trace.ncbi page where you can actually browse for different experiments and just hit search for any key terms that you're interested in. While that is loading up, I will just tell you a couple other things. So once we get to that page, we will search for Coral and Pollock together, so I'll just copy that. Then we're going to download the metadata from this experiment into Excel, or you can use Google Sheets if you prefer. We'll identify relevant sequences because the database that they provided has over 600 samples. It would be around 3 gigabytes worth of data. We'll save the run numbers into a text file, and then we will move that text file into the Ncbi data directory so that we can use it in subsequent steps. After that, I will show you how to create the metadata tab-separated value file for QIIME2. This is what you need for importing your data into QIIME2 later. And then we will go and do the steps required to do the data download. So if you're not interested in working with QIIME2, you can just skip ahead a couple minutes and you'll get to the data download section. So with that done, we've got our data set here. I'm going to go ahead and search Coral Pollock. And if you do this on your computer, you'll just find one data set from Penn State. We'll go ahead and press that little save icon. And here we go. This is what you're probably going to see on your screen as well. You've got metadata below. It has the run number. This run number is what you'd use to look at individual sequences. So we can do that. I can click on that. And you'll see this is the ERR accession number. It is a run that has 2 reads per slot. This likely means that it's a paired data set. So you're doing paired sequencing here, which, don't get too caught up in that detail right now if you're not sure what paired is. But it's essentially when you sequence in 2 directions at once and you get better resolution doing it that way. Then if we press on the data axis, you'll see there's a couple different file types. We've got the SRA file type. You could download this right now from your browser if you wanted to. It's as simple as that. Or you could even download the original data that they uploaded as well. But we're not going to do that. We're going to do it a different way. So we're going to download the metadata. And I'm going to show you that in the Finder here. So this is the SRA run table. And I highly recommend that if you work with data and work with text files that you use Notepad++. This just does a really good job of showing us the data, and it doesn't save the files in a weird format that will cause issues further down the line. But what you can see just from looking at it right now is that there's lots of values, and they seem to be separated by commas. So it's likely that this is a CSV table. And so I'm going to show you how to import this into Excel so that we have all that data. It's pretty simple. You press on the Data tab here, you import from text, you go to the folder where your file is located, so that's in the downloads, and then you press import. Excel is going to do all the detecting on its own, so it's going to figure out, okay, hey, this is a comma, separated values. This is what we think the data set should look like. And yes, I agree, that looks good, so we're just going to load that. It's going to appear, we've got all our data now. You can see the run column, this is the most important column for us. And then we have these other data sets, such as, what kind of assay it is. This is an amplicon assay. What's the length of these assays? It tells you all that. What's the university that provided the data? But we're going to look for a column called title. And this is what we'll use to do some filtering. And essentially what I want is only the coral tissue samples. If you wanted the coral mucus and the coral skeleton, you could do that as well. And then I'm going to go a little bit further over, quite a ways over actually. And I'm going to filter this based on the coral genus. So I want to look at Acropora coral. I want to see what kind of microbes the Montipora have that they looked at. I want to look at the Stylophora and also the Postlepora and Parietes. So then I'll press OK. That's given us 65 results, so that's good. That's more manageable. And now what you want to do is go ahead and select everything here, including the first one. We're going to copy that. We're going to make a Google Sheet. Make a Google Sheets, create a new one, and just paste that into the first row. And there we have it. We've got our 66 rows in total, and we're going to need these run numbers. So I'm going to press Control and Shift and the down key to select this whole data, all this data. Then I'm going to go into my Notepad++, create a new file, and paste it in here. You can see it's a file that only has the run identifier, and that's all we want. So we're going to save this, and we're going to save this all the way at the top. There's a normal text file, so we'll save that. We're going to go on the desktop, which is where, nope, not on my desktop, it's somewhere else. Let me see. I think it's in here, the tutorial, yep. So we're going to put that in the Pollock folder, and we're going to call that coral. Let me actually just double check real quick what we're supposed to call it. We're supposed to call it coral tissue runs. Coral tissue runs.txt. Press save. So now we can close that out, and we've got the runs that we're going to not the runs, but we have the runs that we need for our data download step later. So that means we are good on that step, and we can now move on to creating the metadata tab separated value for QIIME2. So QIIME2 is a little specific in what it likes, and you can learn more about QIIME2's documentation steps and how you're supposed to format the data. A good one is to go to the Atacama soil microbiome tutorial, and then it's going to have one about the metadata. See, the sample metadata is available as a Google Sheet. This is going to be our guide or reference for formatting our metadata in the same way. And you can see the first value it has is the sample ID. So we are going to go to our sheet and rename our run column to sample ID. Then we're going to insert a row below the top column, and this is where we're going to essentially copy and paste the first two values, just like that. And this is almost it. Now we're going to go to the right and just press Control F to find our barcode column. So there's our barcode column, and we're going to drag that all the way over to the left. And we're going to say that this is categorical. And this would mostly be it, but you'll need to classify all of these other columns as well. So go through this metadata file, look at things that you might be interested in. You know, it might be interesting, for example, to keep the collection date. So this would be numerical, or it could be numerical if that's how you wanted to treat it, but it could also be categorical if you're just going to be comparing years. There's different data types out there, and you'll just need to be familiar with them. More numerical would be like a percentage value or a measurement of the coral size, which it has as well. So let's see, centimeters. What might be millimeters? Column maximum diameter universal. So there, for example, this might be one. So we might want to copy these things, because it could be that, you know, with the coral's increase in size, that might affect the microbes that coral has. Although probably we should expect to see more differences just by the species. So these ones, for example, you might want to say that this is numerical. This is numerical, 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 and then numerical, numerical, and that's probably it. Categorical. And for now, that's all I'm going to be including. So I'm going to go ahead and delete the rest of this. But for you, you might not want to do that. You might want to look through these and keep certain metadata that you think is more important. So I've got my metadata table here. We've got the sample ID. We've got the types that they are. And you'll see right now that there is some issues, right, with formatting, at least for this data sheet. But when we download this as a tab separated value, it's going to get rid of all of that formatting for us. And you're going to have issues, I'm fairly certain, with any rows that have no data in it. So either choose to omit those samples or fill them in with NA characters or something of that nature, so that you don't have problems down the road. So now to download this, we're just going to go to the File Downloads tab, download the tab separated values as the current sheet. We were going to show this in the Finder. I'm going to go ahead and cut this out of my Downloads folder and put it into the folder where I'm currently working. And we're going to rename this to Sample Metadata. And it already knows it's a TSV file, so you don't need to add that extension. And that is it. So now we've got our metadata, we've got our run numbers, and now it's as simple as just running some code that I've got highlighted here below. So in this one, we're saying we're getting the rows in the coral tissue run.txt. First, we need to cd into Pollock. Sorry. If you type in ls, that'll list everything in the directory. So here we're going to re-execute that command above by using our up arrows to find the most recent commands that we run. And so we're going to show you what the output is. And you can see it's pasting out the values located in each new line in that text file that we made. Then we're going to use this pipe, and what the pipe does for bash is it takes the output of the previous command and uses it as the input for the new command. And so we're going to be inputting the text file's output into GNU Parallel, which is a program that parallelizes multiple tasks in bash. So it's really, really useful, and if you can spend some time learning how it works, that would really benefit you. And we're going to tell Parallel to start as many jobs as possible, and for each one we want it to run this command prefetch with the input from the previous command. And so I'm going to show you what that would look like by adding the extension --dry-run. And now if I run this command, you're going to see this is what Parallel would have put out. It would have said prefetch this value, prefetch that value. So that looks correct. That's exactly what we want to do. And just FYI, the prefetch command comes from the SRA tools package that you'll install in Conda. And yeah, so let's just go ahead. So it is running the command right now. Ooh, and it's giving me lots of output that I cannot see because I think it's formatting it in a different color. Ah, no, here it is. That's great. So it's downloading the first file. I'm going to just switch real quick my internet connection. Make it a little bit faster maybe. Looks like it's freezing, so I'm going to cancel that. And let's just try this command again. I'll put it in here this time. To paste into terminal, you can use right click. So that looks a lot better. So it's downloading each of these. And you'll see for metagenome files, they're usually not that large. They're like on the order of 20 megabytes or so. So we've got all of our files. If we press ls, type in ls, we can see, here they are. They're all in their own directories. So that's what this green color means on my screen, is that it's a directory. And we can change the directory into one of these files, ERR2816397, and then type in ls again, and we can see, okay, each directory just has one file type, and it ends in a .sra extension. So now we're going to type in change directory, put 2 dots, and that says, hey, go up back 1 level, and that means that we are back in the Pollock directory, or the Pollock folder. The next command I'm going to run is going to find all of the values in the current directory that end in the extension .sra. We're going to print the output of the find command into the new program xargs, and it's going to take the input from before and essentially move that to a new place, and that's to the current directory. So it's moving it from each folder up 1 level. So I'm going to go ahead and run that command. And so now if I type in ls, you'll see, okay, it's moved all of the .sra extensions out of their folder. So now we just want to delete the empty folders. That's what this line is doing. So if I type in ls, you'll see all those empty folders are gone now. And now what we're going to do is convert the .sre files into the Fastq file format, which is what those metagenome files are generally in. And most sequencing files are .fastq. So we're gonna, here it's gonna say list all the files with that end in the .sra extension. Pipe that output. So I'll just show you how that works. So here we go, it's only showing us these. Pipe that output into parallel, start as many jobs as possible, and run the program fastq dump with the argument split files, which is what you need to put if you're using paired end sequences, because otherwise the SRA format will just put them into one file, but what you want is them split out. And then you can add this final extension org fmt, which means original format. And then finally just these two brackets, which is what tells parallel where to put the input from the previous command. So the ls*.sra output is going to go into where these brackets are. So we're going to go ahead and do that. Shouldn't take too long. And that is done. And then we're going to make, so if we look at what we have now we have all these Fastq files. So we're going to make some directories where we'll put the Fastq files and where we'll put the .sra files as well. So I'm making the directory Fastq. Then I'm saying move all the files that end in .fastq into the Fastq folder. So if I type in ls, all those Fastq files are gone now, right? And I'll do the same for the SRA files. Type in ls, and now you'll see there's only a couple values. We've got the Fastq folder and the SRA folder. And that is pretty much almost it here. Next, we were going to go into the Fastq folder. So you can see we have all our Fastq files in here. And then we're going to create a manifest directory because we need to create a manifest file. And I'm just going to show you which one we're going to make. We need to make a manifest file for QIIME2 to use to actually import our reads. Because we're working with paired end sequences, we need to recreate this file right here, where we'll have the sample ID, we'll have the $ symbol print WD, so this means print working directory, and then the file path, the name of the sample, and in our case we're going to end it at .fastq. If you had .gz files, you could end it in .gz. Okay, and then these are going to be tab separated, so you'll have a forward absolute file path and a reverse absolute file path, and that's going to be pretty much it. Now if you're working with single end reads, you would have a similar format, but in this case you would just have one value, one absolute file path. And so you would use this, for example, if you only have single end reads, or if you've had paired end reads and you merge them before using an application like pair, for example. Then you would import it as a single end read when you do all of your data cleanup before you went into QIIME. Okay, so I've created a fairly great program that is going to make the manifest file for me, and it's going to adapt to whatever values our folder has. So I'm in the Fastq directory. Now I'm going to echo this command. So echo is essentially going to say, let's just run this part on its own. Echo, and you'll see echo star paired end Fred 33 Fastq manifest file for forward and reverse reads. Forward and reads. Well, might want to add reverse reads right here. Reverse reads. And all that command does is more or less print what you put in those quote values out onto the screen. And so we're going to add this little, I don't know what you'd call it, kind of like an arrow, right? It's saying arrow pointing that way, and it's going to save the output of that command into the manifest1 text file. So go ahead and do that. And now we're going to see that there is a manifest1.txt file. And I could look at that on my computer in the Fastq folder. Here it is. And you can see, okay, here's my text document. It has the values that the cat command wanted me to print, and it has them on one line. All right, then I'm going to echo another command. In this case, I'm going to add the argument -e. that's going to allow me to put these tab values in there. That's what these are. \t is the tab value. And so we're going to add that. So by having these two little arrows or brackets or whatever they're called, that's saying append the output of this echo command to the bottom of the manifest1.txt file. And I'll just show you. So here we go, we've added that, and you see that these values are tab separated. Okay, then we're going to create some new variables. This variable is the print working directory variable, and I'm running a for loop here, so I'm saying for I, this means whatever value that we're going to find, in .fastq, so essentially any Fastq file, do this command echo print working directory, and then done. And we're saving that as a variable. So if I, for example, put $ print wd, okay, well I'm not, yeah, okay, so what it did is it actually put out this command, $pwd, and it said command not found. That's fine. So we've saved that. Then we're going to do the same for the sample ID. This is just going to find all the sample IDs. Then we're going to get the path and save a certain value from that. We'll get the absolute file path. And this is essentially putting together all those previous values into one line. And then I'm going to use this command, paste all these values. I'm going to remove any tabs from this previous output. So I'll just show you what this output is to make this a little more clear. So here we go, this is the output. Now if I add this second line with the tr delimiter being a tab value, that's what this is, tr-delimiter, that's what that means, then a tab. It got rid of the tab, so you can see that there. And then I'm going to cut away values using the delimiter underscore, so it's going to get rid of this, and by putting -f1 I'm saying keep the first part. So I'll show you what that looks like. Keep the first part, you see? So now we have these values, and it got rid of the extension. And now of course you're going to have repeats of the same code, right? So you've got the same values. So I'm going to use this little addition here, unique, and it's going to keep only the unique values. So now we don't have repeats. And then I'm going to send that to parallel. I'm going to start as many jobs as possible. I'm going to tell parallel to keep the order. So whatever came first should be output first as well. And I'm going to give it the command to echo e this bracket, this value right here. This is saying take the input of the previous command and get rid of the parts where you have the /. And I'm going to show that to you just in a bit. So I'll just try it right now. You see? So we no longer have that path name in the front because it found this bracket and it knew to get rid of everything else. So we just have the unique values. And then I'm going to put a tab between that, and I'm going to put the full path. So this includes printing working directory. So I'll just show you what that looks like real quick by getting rid of this, right? You see it has the whole path value, and then at the end of that I'm adding on my own the underscore and the one.fastq extension, and then I'm going to do the same for the 2. Okay, so why don't I show you what this full command does. And you see it has our unique sample name, it has the first run or the forward data file, and then it has the reverse data file. So the reverse and forward reads are separated by tabs. That's exactly what you need, and then we're going to save that onto the manifest, into the manifest2.txt file. Okay, so now we've got manifest1, which has our first part, We've got manifest2, which has all of the unique values and the paths that QIIME needs. And so the next part is to combine those two text files using the cat command. And then we're going to combine those and output them into the directory manifest, and we're going to save it as manifest.tsv. Okay, so I'm going to run this one. And we can look at what that output. So I can go into the manifest folder, and here's my manifest file. And sure enough, it has put all of the values together. Perfect. This makes it so easy. Like, imagine if you had 600 values. This would do the whole manifest organization for you within a couple seconds. Then we're going to remove all the old text files because we don't need those anymore. And we're going to change directory up one level into the Fastq file. And now we can actually start with our work in QIIME2. So if this is all you needed, congrats. I hope that was useful. For everyone else, I'm just going to keep going for the QIIME data to import. We're going to activate QIIME2 right now using this command, conda activate QIIME2-2020.8. We're going to tell it how many cores it has to work with. So in my case, it's 24 cores. In your case, it might be like 4 or 8, depending on what you're working with, or maybe even 64 if you're running this on a cluster. And now we can actually begin the import. So I'm going to say QIIME tools import. I'm going to tell it the type, and what we're importing is sample data, join sequences with quality. Join sequences with quality. This might not be the right name. I'm not exactly sure right now. So let's just run this command and see if it has any inputs. Join sequences with quality. Because they're not joined. Yeah, it should just be sequences with quality. Paired end sequences with quality. So I'm going to just fix that here because that might give us a mistake. Paired end sequences with quality. We're giving it the input path, which in our case is not going to be reads. So we'll just type ls. So we see we're in Pollock, and Pollock has our Fastq file, so it's not going to be reads. It's going to be, I wonder if I put this somewhere else. Yes, here it is. I'm sorry. So these are just old remnants of a previous code. So I'm going to go ahead and delete this. And we'll just work with this line. So QIIME tools import type sample data paired end sequences with quality. The input path is in the Fastq folder. Within the Fastq folder, it's in the manifest folder. And in that folder, we're going to use the manifest.tsv file. The output path we're going to call demux.qza, and the input format is paired end Fastq manifest Fred33v2. And this took about 4 minutes before, so it could take quite some while on your computer as well. Once this is done, you're going to want to run this next command, QIIME demux summarize. In there, you're going to put the input data, which is the paired, which is going to be demux.qza, this file right here, and we're going to get an output visualization, demux.qzb. And I'm going to go ahead and show you what that output would look like by going to view.qiime2.org. I will go to my previous folder that I did this work in already. Demux.qzb, this means it's a file that you can visualize. It tells you the forward reads, the minimum, the maximum, the mean. It tells you a frequency histogram, and then it provides you with an interactive quality plot. And this quality plot is something you'll want to investigate to figure out where you need to trim your sequences. and you can actually zoom in like this. And so I hope that is useful for you guys for downloading all these data sets. Not too difficult, but it does take some time, especially if you're learning from scratch. And with that, I wish you good luck. Thank you.